logic. So the last video we talked about the interface and about the test bench, how it is. Now we're going to talk about gates or the gate level modeling. So just as a reminder, right, we're trying to implement this state graph, which is represented in the state table. That was from an earlier video. Um, and from another early video, we took that and made Cardinal maps, and we were able to get the equations that we want to implement. I'm going to implement this XOR for the first or least significant bit, and this set of equations for the three encirclements. I'd sum of products for the second or most significant bit. All right. So let's take a look at what we have. Um, so we've got this, I call it Model 1 gates. If you remember, all the things we're going to do is Model 1 underscore and something about the type. The inputs are standard, right? Input clock and reset, and the output is the state queue. But I do it as a wire, not as a reg. The book does this as their kind of particular habit. I don't like it as a habit. So allow me to take the time to kind of mention it when it goes on. So when you do an output reg as a state, there's nothing technically wrong with that. Um, but technically speaking, when you have an output, you should be able to write to it, but you're not supposed to be able to read from it. That's a Verilog spec. Um, Now, what you'll notice in the way the book allows it, which they've noticed that a bunch of the compilers don't actually do that isolation and protection like they're supposed to. So therefore, you can do an output reg and you can read what the current state is and just assign it to it. But that's actually against the philosophy of how it's supposed to be. You should not be able to modify an input and you shouldn't be able to read an output. Inputs are for reading and outputs are for writing. That's really the concept. So by doing an output wire, then what I do is I just assign Q to be the state. And well, that just allows me, I now have an internal state S, which I can both read and write and do whatever I want, and Q follows it exactly. So this is technically the way, according to the standards, you're supposed to do it. So you should actually learn the technical way. If you go to a company and they insist, oh no, you can get away with it and our compiler works, more power to you. Do whatever your company wants you to do, right? You can tell them they're right. I don't care, right? But I want you to know what the safest one is. Because if you ever get another job somewhere else and, they stick more to, the basic standards, then I want you not to be caught off guard when you're dealing with it. Okay. So that's my temporary rant on here and my disagreement with the book. Um, for internals now, how do we do the state? So I set up a register for the state, and then I make a wire for the next state. And I mentioned this inside. This is to follow the format here, right? If you remember, we kind of have these two boxes. The state, which is only going to be your memory, in this case, the flip-flops, and it outputs its state. That goes into the next state logic, along with the inputs, technically. And that it produces the next state value, which goes to state, gets read in, and the process continues. So we want to kind of follow this format. And so that is exactly what you see happening over here. I just instantiate both of those. The next state, which is the output of combinational logic, so it must be wires. And state is going to actually come from changes inside the state, which will implement it in always block, so it must be a reg in order for me to change it in always block. Um, so I kind of put the two state variables together, and then I also set my wires. And these are for intermediaries that go on. So if you look at the equations, I have a number of AND gates that are coming in down here. You'll see there's 1, 2, 3, right, that are AND gates. And so over here, I've got A0, A1, A2, three AND gates. And then I have a not input because two of my, or actually three of my values here have input negated. One, two, eh, sorry. Now, there's my third one. In the case, I'm going to actually use this, if I can select it. Um, I'm going to be using this equation, which doesn't use the negated input. It uses the XOR gate. So I'm technically only going to have two of these negated inputs, but it's still nice to have the negated input so I don't have to, um, you know, repeatedly do things. So I'll just build a NOT gate. And so I need an output of that as well, which I call NIN, not in. All right, so that gets me my three AND gates and my NOT ins. Those are intermediary wires. They never cross the line, either coming from input or going to output. So they are just kind of hidden values inside my system. The first part is not going to change amongst any of the designs. This first part that's in here is actually implementing this part up here, which is a bunch of D flip-flops going in. Um, so what these ones do, so since this is going to do my memory portion, you'll see it's always at, and now I have positive and negative edge. Whenever you see pos edge and neg edge, that tells you are building a flip-flop. The first one is usually the clock. The next one is usually your reset functionality. Um, so at pos edge of clock and neg edge of reset. So that sets up the basics of my interface to this. It tells me when I'm being triggered. Um, Remember, reset is always more important than clock. And since it's on a negative edge of a reset, that means I want to do reset whenever reset goes low. So um, since I want to do it and it has priority, I check if not reset, which means if reset is low. So this is just a fast way to check is reset low. Whenever reset is low, reset is being asserted. Reset always wins. So at negative edge of reset or positive edge of clock, either way, um, and either way of those will give me a reset value that's zero. I just set my S to be equal to zero. So nice, simple logic for that one. And that actually creates them. So if you look at all the other design models, right, the model for the equation version, boom, there is essentially the same exact functionality. It should be exactly the same because I just copied them, right? Or I should say copy and pasted between each one of these. So I took the first one, the always through his end, and I pasted it down here for my equation, which will deal, and then I paste it down one more time. All right. So you can see that's the setup for dealing with our state or our flip-flops. All right. So we've now gone through, we've dealt with the basic interface, initial declarations, given a declaration of stat being high, um, for the pause edge for the clock and reset for that. So that gives me my logic and the output being assigned to a separate wire just to keep things clean. Um, what that leaves now, right? So I have the basically this is the state portion, and state and next state will be the wires going back and forth between these. They're called wire and ridge, but they're functioning as wires. So now I have to say, what is the next state logic? Okay, so I'm going to try to show both of these simultaneously. So, all right. So my next state logic, right? The next state bit 0 is state 1 exclusive OR input. So it's the exclusive OR between those other two bits. So this is actually the first bit, XOR, and it says next state bit 0 and S1 and in. So anyway, this equation right here, boom, is that gate right here. And you can check to see, right? State bit 1, state 1, XOR, XOR, and it uses input, IN. All right, so that is bit 1. Then we'll get to our second one. So I want to implement this set of equations. This will involve a few more gates. You'll notice I've got these two negated inputs. So the first thing I do is I make this NOT gate where I have the negated nin, being being created by the input. So I pass input into the NOT gate and it passes me back nin. Remember, that's a local variable. So it's kind of one of those intermediate states. And then I can now use nin as an input for negative in. Then I'm going to have three AND gates. The first one is going to be negated in or nin and S0. So you see nin S0. That's my second gate over here. My third is state 0 and state 1 ANDed together. So if you look at the second AND gate, you'll see state 0 and state 1. And all of these are producing three different AND gates, right, which are A0, A1, A2. So A2 is S0 and 1. So you can see it does state 0 and 1 on the second AND gate. The third AND gate 2 here, um, it's essentially it takes nin in, right, the negated input, and the S1 bit. So pretty straightforward on that. And then the overarching equation, so that gives me my three. I've got my OR gates that I need to do to combine those three together. So I generate an OR gate here, and I have OR 0. I have my three different AND gates wires coming out, and it generates next state bit 1. So just like the XOR produced next state bit 0, now I've got next state bit 1. That describes all of the gates. That's the equations, right? This one and this one. I built the gates for them. Done. This is the combinational logic, i.e. the next state logic. This is the logic necessary for the state. So those are both check. Oh, this tells me what my output is. So the output that I'm going to do from this module will be just output the state. And I've got these intermediary wires and my state logic. So NS and S. So I've now implemented everything you see in this figure according to these two equations. So now that I have done all of that, it is time to do the fun part, which is the simulation. So I want to simulate Model 1 gates. So you'll see here inside, I have to kind of shrink that up a bit. You'll see inside, we already talked about this test bench on the previous video. I've got Model 1 gates as the device under test immediately. Don't forget these dump vars and this open EP wave. You'll see that happen at the very end. So I'm going to save this just in case I accidentally bump something, or maybe I shouldn't have in case I accidentally bump something. But anyway, we'll save it and then we'll run. And then if you watch the log file, it now is going to run through. It sends me messages, it finishes everything, and it outputs this. Now, I've already kind of set this up to have a basic functionality put inside here. First time you do it, there'll be nothing. What you'll do is you'll click this Get Signals button. So this is only because I've already done some simulations. You'll do the Get Signals, and you'll have options. Right? So if you remember, I made 3 different models. So all those 3 models are um, actually available. Actually, there doesn't show one of them here. I'll have to check and see why it's not showing one of them. But um, so we see that, and we've got Model 1 test and the device under test. So this is the top level module, and this device under test is the particular one I wanted. So what I did is I did um, the top level test module, and then I told it to append all of those. So that's why you see Q clock in and the reset. And then I went to device under test. The device under test will walk through all the different possibles. And what I did is these are all the internal variables. Also, I grabbed this next state since Q is assigned to be equal to S, and I already have that from here. I didn't need the actual state. I just needed the next state logic to look at it. Uh, I didn't pick any of the other internals. You certainly could. So I just came in, grabbed next state, and then said to append the selected at the end of it. That's why next state is at the bottom. So those would be the ones I would recommend doing. The nice thing is, since I picked it from device under test, when you change the device under test, every device under test does have a next statement because that's how I built them all. So it'll just automatically pick that one up, and when I move between them, it'll be nice and clean. Now, since that's the order I put them in, that's the order it's going to keep sticking them here. I want to see next state right next to the actual state variable. So I select the name here, and it'll give me options for that signal here. And so I'm going to do this one, which means move it up in the priorities. I'm going to make it the highest priority at the moment because I want just above the actual state. Um, and then, you know, we can then look at the individual signals. Okay, so now what I want to do is look at the clock. And every time I do a positive edge, that is when, my current value of next state becomes state. So for instance, I see a positive edge here, and since there's a positive edge here, that means my registers will read that 0, what the next state is, and they'll copy them into the state. Now, next state is going to, it will change whenever state changes, um, which is on the positive edge of the clock, or whenever the input changes. Now, my input is going to change whenever, whenever I allow it to, but I did that essentially, remember from the thing that I said, wait 5 and then every 10. So that puts it on all of the negative edges. Since I do the reading at the positive edge, that gives me lots of time to become stable. So when you look through this, you'll see changes can happen twice a cycle due to either when input changes on the negative edge or when a new state changes, which happens on the positive edge. So um, I can then look again, right? So you can see the actual state changes at this point, and it grabs what is the value just before that edge. So it'll take a 1 and it'll change the next value of the state to 1, right? Positive edge, 1 to 1. Right? And you can walk down every positive edge here. You can see it goes 1 to 1. Then at positive edge, it'll take the previous value 2 and that puts it into the next state 2. The second it does that, the value of next state is based on the current value of state, but state isn't reading it. So it doesn't copy this value of 3 over to here. Um, um, it only changes this value here at the or at the value of clock is a positive edge. So you can see positive edge. Whatever was here gets copied over here. Whatever was here gets copied. So you'll see it kind of move down the line every time a pause edge comes in. And I'll notice that it does a nice job of taking whatever that value is and copying it over. Um, your inputs are straightforward. You can actually come back in. It's a little bit easier, I think, to do. Um, oh, if I do, I close thing out. So um, I think it's a little bit easier to do the checking on this off of these, right? So we can see them built. It does a little bit nicer check. Let's run this again. Doop, doop. Sorry, trying to flip between them. Um, so there's my gates, but I want the state graph. There we go. Or the state table. So I'm going to take this state table. Let me run this again so I have my waveform. And I'll shrink this. We all right, so I see a positive edge transition here. And at that positive edge, it reads what is the value at that edge of 0. All right, so boom, up it goes. The next state is valued 0. So it copies that up to the state, and which is 0 right at that instant. Now both were 0 before because that was my starting condition, so you don't notice it. But you'll notice that reset sets it to 0, which it was before, but the input is a 0. So if I'm at state 0 and my input is a 0, I go to state A, which is a 0. So at state 0 on a 0, go to 0. So at state 0, right, at that pause edge, on a 0 on the input, go to state 0. Positive edge, this is when I'm measuring again. So it says at, I've now got state 0 on an input of 1. At state 0, input of 1, it should go to B, which is 0, 1. So at 0, I'm on an input of 1, and it goes, like it tells me to, goes to a 1 at that point. Um, yeah. Then we've got at a 1 on your transition of 1. Okay, it's a little bit easier with these. So you can see whatever the next state is getting copied up. So that's a 1-to-1. See where this gets interesting again. So this is kind of a little bit, you'll see some more rapid changes and they don't all get read. Um, so pause edge clock, right? You know, add a state of 1 with a 1, add a state of 1 with a 1, we go to itself. So that carries over. But now look at this next one. The state doesn't update to here. Again, you see the pause edge clock. So it doesn't update on neg edge clock, which you don't expect, or which you would expect to be true. Um, the input changes though. So it goes from a 1 down to a 0. So my current state is a 1 with a 0 input, and the clock hits. So that's an easy thing to calculate. All right, so I'm at state 1. I'm getting a 0. So I go to C, which is state 2. So you see it get modified up to a 2. DDD. Okay, so anyway, state changes to a 2. The input is right now is still a 0, so state 2 on a 0 should go to D, which is 3. So that's why it calculates a 3 here. But we haven't hit the pause edge yet. So that's not, or sorry, that's the data pause edge. The clock pause edge happens here, which is when the update happens. Um, so the data value pops back up to a 1 in between my pause edge of the clock, so that I'm at a state 2 with an input of 1. At a state 2 and my input, oh sorry, at state 2 with input of 1, which says go to A00, which is what we calculate once that changes, and then we read it and update it in. And you can just kind of scroll down the line. Every time you see a pause edge, I'm at 0, I get 1. Right? Um, so I can check my readings on there, and the state 2 gets copied up. At the next one, right, state 0 gets copied up. State 1, right, nicely copied in. Oops. Right, on the pause edge of the clock, on pause edge of the clock, right, 1 with an input of 0 expects 2, so it goes to 2. All right. I don't know. I'm looking through to see if there's anything interesting in here. I think the rest of this is pretty straightforward. You can just see next state goes to state each time, pause edge. Next state 0 goes to 0, and you can calculate what this next state is just by looking at the table. So you take this value of the state and the appropriate input gives you this. So 2 with an input of 0 goes to 0. 2 within, did I calculate? State 2, 1, 0 with an input of 1. Oh, what am I saying? That's a 0, that's a 1. 2 with a state of 1, right? 2 with a state of 1 goes to state 0. So state 2, input 1 goes to 0. Then current state 0 at the uppick of the clock goes to 0, because just whatever's here gets copied over. Right? At state 1 gets copied over. I'm at state 2, it gets copied, so on and so forth. Anyway, I think that makes sense, and I think you can use this line, right? 1 and a 0, 1 and a 0 tells me I go to C, which is 2. 1 and a 0, I go to 2. Okay, so you can kind of see calculation of the next step here and then updating of them. So this kind of gives you that nice, quick, easy way to check through. Anyway, I have zoomed in quite a bit. just because it makes it easier on my old eyes. You can walk through the waveform and see what you want. When you are done with it, there is, at least there's supposed to be, I'm not seeing it right now. There's supposed to be a little checkbox in the upper corner. Yeah, we, oh, it looks like my computer's having fun. Um, anyway, I'm done with this. I'm gonna stop the recording and try to get my computer to not freeze. Of course, it wasn't having any of these problems until I started running it. Might actually be the recorder's taking up too much time of my processor trying to go through because some of this stuff has lagged. Anyway, hope this helps on both reading the time charts and comparing the time charts to the state. That's a really important skill. And verifying our gate level design. Um, both we saw in the last one that it carried off the idea, and then here that it's actually doing what our state table says it's supposed to do.